working in it, and I try to connect with them and see if we can develop some very good special issues based on the aim and scope of the journal. So in this process, I had contacted my teacher and my collaborator, Professor Panigrahi, because he's been extensively working on quantum information and related areas. And I've asked him to help me acquire a special issue in quantum technologies. So, and this is for a new journal, open access journal, and titled Physics Open. So this journal publishes many things related to physics, and it's a very broad scope area. And we are trying to bring up this very young journal. So we want some quality content. And this special issue is going to deal with anything related to quantum computation. It could be devices, it could be theory, it could be simulations, anything. So anybody who is interested in submitting their papers, they can contact me or Dr. Panigrahi, who is Professor Panigrahi, who is the managing guest editor for this special issue. Please feel free to ask me, reach out to me or him for any questions on this special issue. Yeah, thank you.
Thank you, Srilangani. Now Sibasish has joined.
Yeah.
You can proceed from here forth.
Okay.
Ma'am, you can formally introduce Professor Ghosh and then.
Yeah. So we begin our session today, and our first speaker is going to be Professor Sibasish Ghosh, and he is currently working as a professor in the Optics and Quantum Information Group at the Indian Institute of Mathematical Sciences, IMSC, Chennai. And he's also a principal investigator for the project titled Quantum Heat Engines. So his research interests lie in the area of quantum information, computation and communication, foundations of quantum theory, open quantum systems, quantum thermodynamics, and quantum optics. Today, he's going to give us a talk on quantum homogenization in Markovian and non-Markovian collisional models. So, Professor Ghosh, if you're ready, I can hand it over to you. I guess we'll take a little while. Yeah.
Hello.
Hello.
Can you hear me?
Yes, Professor Ghosh, we can hear you. Yeah.
Sorry for this. So I'll just start within a minute.
Sure.
Okay?
Sure. Yeah.
I'll just how to share this thing? Yeah, share. I have this file.
No problem. Here, you did. Window.
Oh, we have not yet opened. Shall I open this thing? This one.
Okay, we'll put at a screen. Okay.
Can you see the screen?
Yes, we can see the screen. Yeah.
Can it be made full screen? Okay. The screen is moving?
Yes, it is. It is.
And can you see my cursor also?
Yes.
Okay. So I'll just start within a minute.
Yeah,
Sorry
sure.
Okay. Okay, so what I'm going, so let me thank the organizer for giving me this opportunity to talk about some of my works. Sorry for this technical glitch. I had to actually update the Zoom. Anyway, so So this is, I'm going to talk about what is known as quantum homogenization. And this is a generalization of the idea of thermalization, which we are aware of. And so what I'll talk about here is homogenization both for a memoryless open system dynamics, namely Markovian dynamics, as well as for a particular class of non-Markovian dynamics. And the method that I'll adopt here is what is known as collisional model. Okay, so this is the work which was done back in 2020 January, but it has been revised, and also some ongoing work. So this talk is based on both of this. Okay, so let me try to motivate. When you have a system, quantum mechanical system, which is contact with a heat bath, be it quantum mechanical or classical, generally the system will reach thermal equilibration. Okay, and this process of thermalization, classically, we don't ask such questions generally, that how the thermalization happens. We have some phenomenological idea. But in order to describe it for the quantum mechanical system, we'll have to understand first that what is actually the process for thermalization. And in the way, even if a system does not thermalize, maybe it will reach at a steady state, which is a non-equilibrium steady state. And how does it happen? So basically, this microscopic description of thermalization, it has a rich history, and starting with this Boltzmann's transport equation in the context of classical statistical mechanics. And in the quantum domain, when we talk about thermalization or its generalization, namely homogenization, we'll have to look at what is the time evolution rule or dynamics of the state of the system. So unlike in the case of closed quantum system, where the system evolves under some Hamiltonian and which is governed by Schrodinger equation, for a system which interacts with its environment, which is known as open quantum system, we don't have in general a closed form and an equation of motion of the state of the system. That means dynamical equation. So and why is it the case? Because we don't have precise knowledge about the environment, which sometimes we also call as heat bath, and also the interaction between the system and this environment. So both of these contribute to not having in general a closed form dynamics. But this problem that we have problem in having a closed form dynamics has been circumvented in a special case by Gorini, Kosakowski, Sudarshan, and independently by Lindblad back in 70s. And what they have used is that they used certain approximation, which is called Born, Markov, and rotating wave approximation, to come up with a closed form dynamics, which we call master equation. And in this particular case, it is called GKSL master equation, named after Gorini, Kosakowski, Sudarshan, and Lindblad. So this GKSL master equation has the property that although it was derived under certain approximation, namely this Born, Markov, rotating wave approximation, nevertheless, it guarantees that the dynamics is completely positive, which is a demand for any valid quantum mechanical evolution. So this is a CPTP map, completely positive trace-preserving map. But, and also, the thing is that it is such a dynamics which increases the entropy of the system. Okay, so entropy is ever increasing. So if I look at the entropy, increasing rate, so this is always positive. I mean, the time derivative of entropy is always positive. So unfortunately, because it is based on certain assumptions, as I mentioned earlier, this GKSL master equation cannot capture a variety of realistic open system dynamics, and those one which has basically memory, that is non-Markovian dynamics. In fact, historically, people tried to figure out a closed form master equation for a non-Markovian case where you have memory effect, that is system interacts with heat bath and heat bath also interacts with system, and thereby there is a change in state of the system, change in state of the heat bath, and then there will be back action from the bath to the system, and so on and so forth. So this is the generic case. So this time non-local Nakajima-Zwanzig equation was the first approach to to deal with non-Markovian dynamics with memory, but this is a horrendously difficult equation. You cannot even think of solving it numerically, forget about analytically. And so the question of establishing the CPTP-ness of the dynamics is beyond, you cannot do that basically. Okay. So alternative approach which people started with, in fact, this is interesting that this collisional model approach to open system dynamics was first proposed by some Indian physicist, Jayasita Rao, back in 60s, I guess. Okay, and now in the recent times it has taken a lot of momentum, and and then so what is the idea behind this for this collisional model, which I'll call CMs? So you have bath or environment, which we consider here to be made up of identically prepared subunits or ancillas. So for example, if I have a heat bath, generally which we consider to be a large one with various degrees of freedom, in the collisional model, we assume that this heat bath consists of, let's say, a large number of single qubits, large number of qubits, okay, each of which is prepared in some particular initial state, which may be thermal state. And among these qubits, bath qubits, there may be some interaction, there may not be some interaction. They may be prepared initially in completely uncorrelated state, or they may be prepared initially in some correlated state, so on and so forth. All these things can happen. And then in the collisional model, what we assume is that my system interacts with these individual qubits of the heat bath one after another. So my system interacts with the first qubit, then it interacts with the second qubit, then it interacts with the third qubit, so on and so forth. And in between, I can either cut off the interaction with the previous qubits, or I can keep it. I can, keep it as it is. Okay. Now, this process of this collisional model approach is interesting in the sense that you don't have to take extra initiative to prove the complete positivity of the dynamics of the system. Why? Because we know that the system interacts with the heat bath, first qubit of the heat bath, which is through some unitary evolution. Then it interacts with the second qubit of the heat bath, which is through unitary evolution, so on and so forth. So initially there is no correlation between the system and the bath qubits. Therefore, it has to be a completely positive dynamics of the system. Okay, and here is no approximation like what people have used in deriving the GKSL master equation. Okay. Now, when I take, let's say, a bosonic bath, that means a system of harmonic oscillators, and when I take a dipole type interaction of the bosonic bath with, let's say, a charged particle or something like that, or some atomic levels, two-level atoms, then one can easily come up with a Markovian collisional model. How? And this is what it was done in this work, Quantum Measurement and Quantum Meteorology, in 2017. And this is, so how can one figure out that this can be cast as a collisional model? So basically you go to the Fourier domain. So initially it was in the usual domain where your atomic level is interacting with all the harmonic oscillators of the heat bath. And now what you do, you go to the Fourier domain, And here in the heat bath, you don't assume that the harmonic oscillators are interacting. Also, don't assume that they have any correlated state to begin with. So when you go to the Fourier domain, that means in the frequency domain, then what you will see is that basically, well, not frequency domain. Actually, you will have initially in the frequency domain through the interaction, and now you go to the Fourier domain, which is time domain after Fourier transform. So you will see that your system, which is, let's say, two-level atom, it interacts with individual harmonic oscillators for certain time window, and then the atomic two-level atom will interact with the next harmonic oscillator in a next time window, so on and so forth. So it will eventually give rise to a collisional model kind of approach. Okay, right. So and this collisional model approach has been quite successful in studying the different properties of quantum thermodynamics, which is not very easy otherwise. And in fact, it can also address this collisional model approach to open system dynamics, also address problems like relaxation to equilibrium. How does the system relax to equilibrium? The link between information and thermodynamics, which is a quite hot topic nowadays. The efficiency of thermodynamic cycles in multi-level engines, and quantum battery charging, study of non-Markovian effects, so on and so forth. Okay. In fact, collisional models are also used to understand fluctuations of, like fluctuation of some thermodynamic quantities in quantum thermodynamic machines. Okay, like, if I want to look at coefficient of performance or power of a heat engine, I can use this collisional model. So it is quite successful. So the basic philosophy is that, and this is what people working in the collisional model, they believe, that any sort of non-Markovian dynamics, provided it gives rise to a completely positive trace preserving map, it can be realized through a collisional model. Okay, this is the basic philosophy. Now, we don't have any proof of this so far, and that is why people are exploring different cases of non-Markovian dynamics. Okay. So this is how we deal with collisional model. It is a simple-minded model because you don't assume interaction of your system with the heat bath as a whole. You take interaction part by part. So such a simplicity of collisional model, it is advantageous to study non-Markovian dynamics. ANM is non-Markovian dynamics by some modifications in the basic model, as I said. Basic model means where you have Markovian dynamics. So in Markovian dynamics of collisional model, your system interacts with the first qubit or harmonic oscillator of the bath. You cut the interaction. Then your system interacts with the second qubit or harmonic oscillator of the bath. Then you cut the interaction, so on and so forth. So this is how a Markovian dynamics emerges. Why Markovian? Because there is no memory effect. So that the system interacted with the first qubit of the bath, has no information with the second qubit of the bath, third qubit of the bath, so on and so forth. So therefore, there is no question of back action, and that is why it is a Markovian dynamics. Okay. So now, how does one generalize such a simple-minded Markovian collisional model to non-Markovian one? There are several ways. One can introduce, as I said, ancilla-ancilla interaction. One can use initially correlated path. One can use composite collisional model. That means your system collides with heat bath qubits, and at the same time, your system also has interaction with some ancillary system. Okay, or through multiple collisions of the system with each ancilla. That is also possible. Okay, unlike in the case of Markovian one. Okay. So, so the first work, as I said, the first work was done by Jayasita Rao, but that collisional model can give rise to Markovian dynamics was first done, in analytical form, and thereby they spoke about the thermalization process. That means the system will eventually thermalize. was done by Buzek, Giza, and others in these two papers, PRL and PRA, through a more general process called homogenization. As I said, homogenization is a generalization of thermalization. Homogenization is a process to which the system state transformed to the same state of the identically prepared ancillars. So all the ancillar qubits, means bath qubits, are prepared in one and the same state. And homogenization means your system qubit will eventually have that state and the limit of infinitely many collisions. So this is what is homogenization, which is definitely a generalization of thermalization. And in particular, Zeeman et al., they have shown that for a qubit system interacting with qubit ancilla. So when I say ancilla means bath qubits. Partial swap is basically you you take swap operator as your Hamiltonian and then generate a unitary with that Hamiltonian. So that is what is known as partial swap. So which is again a unitary operator. So the partial swap is the unique system ancilla unitary, because you need interaction of system and ancilla, for which homogenization is achieved regardless of the initial state of the system as well as initial state of the ancilla. So this is their what, the Zeeman et al.'s work back in 2002. And then recently, Komar and Landy, they have shown that homogenization does not happen in a specific non-Markovian scenario where you assume that the system, the bath, the ingredients, that mean bath qubits or bath harmonic oscillators, they are all prepared initially in a correlated state, so that individual bath, these qubit or harmonic oscillator states are all same, one and the same, but they are correlated. So in that case, homogenization does not happen. Of course, they have used a particular kind of correlation. One cannot say that this will be the case every time, that homogenization will not happen, but a particular kind of correlation will not give rise to homogenization. So the question is that does homogenization happen in a collisional model scenario where instead of ancilla correlation, you assume ancilla means bath qubit correlation. You assume that there is interaction between the bath qubits. Okay. So we'll show that this happens. It can happen. It can give rise to homogenization, but it will be in general a non-Markovian process because you have bath interaction, and which will give rise to memory effect in general. Okay, so this is the outline. So I'll briefly outline the framework of collisional model, and then I'll go to this homogenization in Markovian collisional model, and then I'll talk about homogenization is non-Markovian collisional model using something called partial swap. I'll also consider a generalization of partial swap, which we'll call partial S theta phi. For particular values of theta and phi parameter, it will give rise to the swap. Homogenization in non-Markovian collisional model using this partial S theta phi. And then we'll compare the homogenization rates for partial swap and partial S theta phi, and then I'll conclude. Okay, so collisional model, maybe I'll just go to this picture. So you have your rate thing, which is system qubit, and this can happen not necessarily for qubit. You can take any system, but for our purpose, we have taken this system to be a single qubit, and individual bath particles like B1, B2, B3 are also qubits. Okay, so system qubit interact with the first bath qubit B1 through some unitary SB1. Okay, then next stage, you cut this interaction, and then system qubit interacts with the second bath qubit B2 through the interaction USB2. In principle, USB1 and USB2 can be different, but for our purpose, we will take all of them to be same. So this provides you the Markovian collisional model. Okay, and basically what happens if I take this USB as partial swap, then the system qubit will eventually have the state which is the initial state of each of these bath qubits. So each of these bath qubits are prepared in one and the same state. So this system state will also have that for large n, large number of collisions. Okay, so this is basically the idea. Okay, so basically you see that your joint initial state of the system and the ancilla consisting of subsystems. So B1, B2 are basically qubits. So this is the joint state, initial state, sigma 0, which is rho S0, tensor product rho 0 B1, rho 0 B2, etc. Where rho S0 is any state of the system, while rho 0 B1, rho 0 B2, 0 means for time t equal to 0. All of them are one and the same state, which we call as eta. And the entire duration of the dynamics, 0 to t, t can be anything, this S and B1 interaction occurs through this during this interval 0 delta 2 through this unitary SB1. SB2 interaction occurs during this interval delta t twice delta t through this unitary SB2, so on and so forth. And here n times delta t, the small time interval, is equal to your time t with n very large and delta t very small. Okay? So that is the continuum limit. And as I said, at the end of the interval, jth interval, j minus 1 delta t, j delta t, this time interval, S is disconnected from Bj. So this is the scheme, as I mentioned here. Okay, good. So now I evolve. So what is our SBJ? It can be in principle system Hamiltonian plus jth bath qubit Hamiltonian plus the interaction Hamiltonian VSBJ, and it works for delta t time. Okay, and so that will give rise to the basically the unitary. So after n collisions, the joint state of system and n bath qubits, it will become like this sigma n. So your initial system and bath qubit state is sigma 0. Apply this SB1, then apply SB2, so on and so forth. And after n collisions, the state of this system becomes, so you'll have to trace out all the bath degrees of freedom. So B1, B2, Bn, which we call rho ns, and you can show that this is nothing but, apply SBn to rho n minus 1s. That means the state of the system at n minus 1s step, tensor product eta, which is the fixed initial state of every bath, and this you can call as a map xi n acting on rho s n minus 1. And the xi n is given by this one. Rho n rho s is this, which is a CPTP map, and basically you can show that the map, CPTP map, are acting on rho s 0 after n collisions, which I call lambda n, is nothing but nth power of xi, and therefore it is a Markovian one. It has the semi-group property, etc. So it's very simple. Okay, because semi-group, because this lambda n can be taken as lambda m concatenation with lambda n minus m. So all of them are completely positive trace preserving map. Therefore, lambda n for each n is Markovian. So this is the Markovian model. Okay, now what about the non-Markovian model? So let me look at this figure first. So your system S interacts with the bath qubit through this USB1, which in principle can be for this partial swap. Then you cut down this interaction and allow the first bath qubit to interact with the second bath qubit B1 and B2 through this UB1 B2, which is another unitary. Then what you do, you can also cut down this interaction, or you can keep it as it is. But next thing is your system interacts with this second bath qubit. So you see that through this first interaction, S with B1, information about S has been transferred to some extent to B1. So as a result, when B1 interacts with B2, that information about S, at least a part of it, will get transferred into B2. So therefore, when B2 interacts with S, B2 already has some information about S. So this is why it's a back action or memory effect. Okay, and therefore this is a generic this is basically a non-Markovian collisional model because of this back action. Okay, so what is the actual thing happening? So initial joint state of system and the n bath qubits is as usual like this. Rho is tensor product n copies of eta. So first S and B1 interacts via this unitary. S is then detached from B1. Thereafter, B1 and B2 interacts via this unitary U B1 B2. B1 is then detached from B2. S then interacts with B2 via unitary SB2. S is then detached from B2. Finally, so this is so on and so forth. Now here, if you look at carefully, the state of the system after nth collision, it will be, of course, a completely positive map phi n, but you cannot write it. It will not have the semi-group property. So that means you cannot write phi n as a composition of phi m and then phi n minus m. You cannot do that. Okay, right. So now in this case, if I look at this figure, there can be several possibilities. One is that when S interacts with B1, I cut the interaction and then allow B1 and B to interact, and then again cut the interaction, then allow S and B to interact, so on and so forth. This is one strategy. What you may have is that, look, S interacts with B1, I don't cut their interaction, then allow B1 and B2 to interact, okay? Then only I cut, S from everything, okay, from B1 and etc. And then allow S to interact with B2. So this is another strategy. Third strategy can be S interact with B1, you don't cut their interaction. Allow B1 and B2 interact, you don't cut their interaction. But now you allow S to interact with B2 and then you cut everything. Okay. So there can be three such strategies for non-Markovian case, and so this is basically the strategy that I mentioned. And so the scheme one is you take trace over the j minus 1th qubit after S interacts with this bj minus 1, but before bj minus 1 interacts with bj. Okay, so in this case you can figure out what will be the state of the system after jth collision, and so on and so forth. Okay, so this is one particular way. Second scheme is take trace over bj minus 1 after it interacts with bj, but before bj interacts with s. So this is a second strategy. You can figure out that there is some difference also with respect to the first strategy. Third one is take trace over bj minus 1 after s completes its interaction with bj. Okay. Now, the thing is that this is interesting. It follows, one can show it easily, that the system state of the system qubit after jth interaction in both scheme 2 and scheme 3 are same, and therefore the system dynamics is one and the same in both the schemes 2 and 3. Okay. But of course this dynamics is non-Markovian. Okay, so we describe this collisional model for Markovian dynamics. We also describe collisional model for non-Markovian dynamics. Now what we are going to do is to describe how homogenization happens for Markovian model, although it has already been done by other people, but just for completeness I will tell you, and then we'll come back to the homogenization problem for non-Markovian collisional model. Okay. So as I said, homogenization means ultimately the state of the system will be same as initial state of each bath qubit. So if rho Sn is the state of the system after its collision with the ancilla qubit Bn, and eta prime k is basically state of the kth bath qubit, okay, after this interaction. So u s bk, rho sk minus 1, tensor product eta, etc. So this is the state of bk after its collision with s. Then for each delta positive, there exists a positive integer delta, n delta, such that the distance between rho Sn and eta is the initial state of each of the bath qubit, is less than equal to delta for all n greater than equal to delta. Okay, and of course also the distance between the kth Bath qubit after its collision, eta prime k, and the initial Bath qubit state eta is also less than equal to delta for all k, 1 to n. Okay. So as I said, Zeeman et al. Have shown homogenization for the Markovian case, and also thermalization later by this Skarani et al. And as I said, homogenization demands that as I take n number of collisions, capital N going to infinity, the state of the system qubit should be equal to the initial state of the Bath. And the here also, if I trace out the Bath qubit, this is so therefore this is the thing. If I trace out the kth Bath qubit, you should get the which is state of the system. That usually the case, time evolved state. And if I trace out the system qubit after kth collision, I'll get the state of the kth Bath for all rho. So homogenization basically that is what you will have. Okay, and it was the Zeeman et al. Who have shown that the unitary, which will create this Markovian collisional model, which will give rise to homogenization, will have a unique form, this USBK. And as I said, I assume that USB1 is same as USB2, etc. And what they have shown is that USBK has this particular form. So this is nothing but exponential of I alpha times this swap operator, 4 by 4 matrix swap operator, which I call partial swap depending upon this angle alpha. So this is the swap operator. Okay, this is a kind of Hamiltonian. Okay, so in case the initial state of the individual Bath qubit is a thermal state, then for each ancilla qubit, all with same temperature, you will have this as a thermal state. Okay, and therefore this rho thermal is an invariant state of this, so it does not change under this evolution. Okay, which is the case for Lindblad evolution, because you have a unique steady state there. Okay, so now how do you prove the homogenization? Maybe I'll just go through it a little bit. So how will you prove the homogenization? So let us take arbitrary state of the system qubit, which is like this. So half identity, 2 by 2 identity, plus k0 vector, which is a block vector, dot sigma. And the jth ancilla qubit is eta j, which is like this, which is eta. So therefore the block vector Lj is one and the same, L1, L2, L3, all are same as L. And the state of the system after n collisions, let us call is at rho is n, which will be again of this form, where kn is the block vector after n collisions. And this state of the ancilla, nth state of the ancilla after this collision will be of this form, ln1, because you have done the collision. And one can figure out what is kn. Kn is of this form, cos square alpha kn minus 1 plus sin square alpha ln. Ln is the original one, plus sin alpha cos alpha ln cross kn minus 1. And ln1 also you can figure out in this form. And as a result, you can show that the ratio of the square of the distance, kn minus l distance square divided by kn minus l distance square is less than 1 whenever I take this angle alpha for the partial swap lying strictly between 0 and pi. And therefore, by ratio test, because this is less than 1, by ratio test you can show that this kn vector, the block vector of the system qubit, which will go to, it will basically lead to L as n tends to infinity. And similarly, ln1 also goes to L as n tends to infinity. So therefore, you have achieved homogenization. So for the Markovian model of collisional model, homogenization happens quite simply. Okay, so let us talk about the homogenization in the non-Markovian case, where the interaction between system qubit and ancilla qubit or Bath qubit is again partial swap, and the Bath qubit interaction. So the neighboring Bath qubit interaction is again partial swap, maybe with different angles. Okay, so this USBJ is partial swap depending upon angle alpha, and U Bj Bj plus 1, the neighboring bath qubit interaction, is partial sub with angle delta. Okay, so by using the same process, what I mentioned there, so you start with initial state of the system, and then jth ancilla initial state eta j, which is same, each of them are same, and therefore block vector also same. And after the system collides with the nth bath qubit, the state of the system will become like this. Again, the kn is the block vector, and state of the nth bath qubit after it collides with bn minus 1, nth n minus 1th bath qubit, will be this eta n0 with this ln0 as the block vector, and the state of the nth bath qubit after it collides with the system, because in the non-Markovian case, bn first collides with bn minus 1, and then bn collides with system. So there the state of the nth bath qubit after it collides with system will become eta n1 with the corresponding block vector ln1, and state of the bath qubit bn, nth bath qubit, when it collides with bn plus 1. So you have basically 3 consecutive processes you'll have to consider, which is eta n2, and the corresponding block vector is ln2. So we'll have to keep track of this kn, ln0, ln1, and ln2. All these 4 block vectors we'll have to keep track in order to figure out whether homogenization happens or not. Okay. So for n greater than or equal to 2, that is the number of collisions greater than or equal to 2, one can figure out what is the expression for kn. That means the block vector of the bath qubit after nth collision. What is ln0? What is ln1? What is ln2? All these things one can figure out easily. Okay, so that is fine. Now let's assume that this ln0 approaches L as n going to infinity. This is our assumption. If I assume that, then by ratio test again, one can show that the other 3 block vectors, kn, ln1, ln2, all of which will tend to L, the initial block vector of the individual bath qubit, as n tends to infinity. And in fact, the converse is also true. If these 3 block vectors kn, ln1, ln2 approaches L, each of which L, as n tends to infinity, then you can show that ln0 also approaches L as n tends to infinity. Okay. In fact, there is nothing special about this ln0. If I instead replace ln0 by kn or ln1 or ln2, same thing will happen. So nothing special about it. Question is that this is a conditional proof of homogenization. Question is, can I prove unconditionally? Or in other words, how can I prove that ln0 approaches L or any of these? Kn approaches L or ln1 approaches L or ln2. How will I prove that? Okay. So this is the question. How will I prove that Pn approaches L? Pn can be any of these 4 block vectors as n tends to infinity unconditionally. Now here is something which I must confess that we tried a lot to have this unconditional proof, but so far there is no success. So for that reason, what we have done is here we have taken help of numerics. Okay. So with minimal numerical support, we can manage to prove that yes, this homogenization happens. Okay. Right. So what is that minimal support? That is, what is that assumption? So what we assume that if the your initial state of the system is is a pure state along minus z direction, or along plus minus x direction, or along plus minus y direction, and if you have plus z also, you can take plus z direction, but that happens automatically. So if we assume that along these 5 directions for these pure states, initial pure states of the system qubit, if homogenization happens, if this is the assumption, then one can prove homogenization for all other states of the system. Okay. So this is basically the idea. Okay, so I'll not go through the proof of this because basically it depends upon this validity of homogenization for an L implies the same for rotated version of L, and also validity of homogenization for an L. L is the block vector of initial Bath qubits, implies the same for scale version of lambda 1. So therefore, homogenization happens for arbitrary state of initial state of the system after I make this assumption that homogenization happens for pure states of the initial pure state of the system along minus z direction, plus x direction, minus x direction, plus y direction, minus y direction. Okay. So if I look at the plot, you see that this is the fidelity. So fidelity means, you know, you take the overlap of the initial state of the Bath qubit and the time evolved state of the system qubit. Okay. So this green line corresponds to the initial state of the Bath qubit, which is basically the pure state along plus z direction, and the dotted red curve corresponds to initial state of the this is Bath qubit is fixed, of course. Here we have what we have taken. This is for the initial state of the, so this green line, this blue line is for the system qubit, initial state of the system qubit, which is along the plus z direction, pure state, and the red dotted line corresponds to the fidelity for the initial state of the system qubit along minus z direction, pure state. So you see that the fidelity, that means the overlap between the initial state of the Bath qubit. So initial state of the Bath qubit I have chosen to be along the z direction. So basically it is the plus z plus 1 eigenstate of sigma z. So L is equal to plus z. So that is the initial state of the Bath qubit. And then for that initial state, if I take the fidelity of the time evolved state of the system, you see that the blue line gives rise to 1, which is expected. So there is no change on the state of the system when it is plus z, when it is the pure state along plus z, and the fidelity approaches 1 eventually when the initial state of the system qubit is a pure state along minus z. So it approaches this 1 value. Okay. So homogenization basically happens. So other parameters like alpha and delta are given in this figure. Okay, good. So next is that you again take the initial state of the Bath qubits to be whose block vector is along z, a unit vector z. So that means the QIQT0 state. But now you take the initial state of the system qubit. This blue line corresponds to the pure state along plus x direction, and red dotted line corresponds to pure state along minus x direction. This is for system qubit. So you see that the fidelity again. So when I say fidelity, as I said, it is the overlap between the time evolved state of the system and the initial state of the Bath qubit, which is QIQT0. So if I look at the overlap, the fidelity, look at here, it is kind of oscillating, and then finally it reaches value 1. Okay. So what is it that we have established? Okay. So next one is the Y. Again, you see that it basically the fidelity reaches 1. So homogenization happens. So these three plots guarantees, therefore, that homogenization happens if I take the initial state of the system qubit along as pure states along plus z or minus z, plus x or minus x, plus y or minus y. Once we have established this numerically, then proving homogenization for arbitrary initial state of the system, pure or mixed, whatever, is easy. One can prove that. Okay, good. So now the question is, in these plots we have chosen particular alpha and delta, the angles for partial swap. What about other things? So yeah, that again you will have to do numerically because you cannot do it so much thing analytically. And this is the plot. You see, we have taken n is equal to 2000 steps. So the number of collisions is 2000, and 10 to the power 5 sets of randomly generated values of alpha and delta. You see that basically, if you look at, this is the fidelity value from 0.98 to 1. So there is accumulation of points along this line 1. Okay, so basically, it tells you that for all alpha and delta, homogenization happens. Okay. So now let us look at so this was for the bath qubit interaction to be again partial swap. Now let us take as I said, we have 3 schemes. Scheme 2 and 3 will give us the same state. So we'll have to compare with scheme 1 and scheme 2. So you see that here is the initial state eta of the bath qubit is a pure state, and system qubit is also a pure state. And then you see that this blue line corresponds to the Markovian one, that means there is no bath interaction. These red and black lines are for non-Markovian scheme 1 and scheme 2. So you see that again it approaches 1 value in the large n limit, but before that it oscillates, and this is a typical of non-Markovianity. So it's a kind of showing a backflow is there. Okay, and right now if I take a different state of the ancilla, ancilla means the bath qubit, which is a mixed state now, and you see that non-Markovian one is this blue dotted line. Non-Markovian scheme 1 and scheme 2 are the red and black dotted line. So there is no jiggling. So there is no backflow here, even if it is non-Markovian, but it ultimately reaches. So it homogenizes. Okay. So now let us look at the so that was for partial swap interaction between bath qubits, 2 bath qubits. Now let us look at the partial s theta phi. So the interaction bj plus 1 u bj plus 1 is of this form, cos delta identity plus I sin delta s theta phi, which we call partial s theta phi, and s theta phi is a particular kind of Hermitian operator, which for theta is equal to pi by 2 and phi is equal to 0, which is the swap operator. Okay, so you can again look for the homogenization condition. You can again assume that homogenization happens for initial state. Well, here there is some issue. Here the initial state of the bath qubit cannot be arbitrary. It should be diagonal along the basis of sigma z. Otherwise, homogenization does not happen. And secondly, if I assume now that the homogenization happens for initial system states along plus z minus z, pure states, plus x minus x, and plus y minus y, all pure, then homogenization happens for every initial state of the system, provided we take the initial state of bath qubits to be diagonal along sigma z basis. Okay, so same argument will work. Okay, so now here is the plot. You see that this plot tells you that yes, indeed, homogenization happens for initial state of the system to be along plus x minus x plus and plus y minus y. Okay, in fact, yeah, this is okay. So here you see everywhere that actually homogenization happens. Ultimately, the fidelity reaches 1. Okay, so this is for partial s theta phi. So here you see that nowhere there is jiggling, only this black card there is some jiggling, so which is reminiscent of the non-Markovianity. You can also see that homogenization happens for other initial state of the ancilla, namely along plus y minus y and other things. Okay, so these 2 pairs of curves are for for two different values of theta and phi. In the earlier curve also for 2 different values of theta and phi. So here also you see in the black curve there is some jiggling, which is reminiscent of non-Markovianity. Okay, now if I take plus z minus z, initial state of the bath qubit, homogenization happens, but there is no jiggling. Sorry, how much time I have?
You have 5 more minutes, Professor Ghosh.
Okay, fine.
Yeah.
So
since we started late.
Sure.
Yeah.
Okay. So now we compare the rates of homogenization for the partial s theta pi interaction between path qubits and partial swap interaction between path qubits. Remember that when you have partial swap interaction between path qubits, there is no restriction on the initial state of the path qubits. Only for partial s theta pi we have this restriction. Okay, because otherwise homogenization will not happen there. Okay, so so what we have done is we have taken, for example, the initial state of the path qubit to be this diagonal one. As I said, we'll have to take diagonal one for homogenization to happen for partial s theta pi, and partial swap we'll have to also take that to have a good comparison. Okay, so you see that if I look at the fidelity, this rate one, the top one, is for Markovian one. That is, there is no interaction between path qubits. The blue, the green dotted one is for non-Markovian scheme one with partial s theta phi for particular values of theta and phi. This red one, the black dotted one is again for partial s theta phi with another set of values of theta and phi. And this non-Markovian dynamics, because my system qubit will spend more time by interaction by interaction of the path qubits together, system qubit will spend more time to homogenize. So it is believed that the rate of homogenization for non-Markovian case in this collisional model will be lower than the Markovian case. But you see here, at least we have one example where the rate of homogenization is same as the for Markovian case and non-Markovian case. In fact, we can see even more that, of course, this is for a particular state of initial state of the system. We can see examples where the rate for homogenization for partial s theta phi for specific choice of theta and phi can be even higher than for the Markovian case. Okay, and so these are different cases, so I'll not go through all these details. So what we have seen, therefore, is that homogenization rate of partial s theta phi is never less than partial swap. But depending upon the values of theta and phi and choice of eta, eta is the initial state of the path qubit, it can be higher, almost same, or lower than the Markovian counterpart. Thus, this partial s theta phi can achieve faster homogenization rate than that of partial swap. And faster homogenization in particular means faster thermalization. Okay, and of course, to compare between Markovian and non-Markovian scenarios, we'll have to choose same alpha and delta in both cases. Otherwise, alpha and delta are the angles. Otherwise, it doesn't make sense. So, for example, you know that if we choose a non-diagonal initial state of the ancilla, namely this one, eta is equal to half, projection on 0, and then 0 k, k 0 bra 1. So, this is a non-diagonal state. You see that the homogenization does not happen. So, you have basically fidelity which is going down. Okay, good. So, let me conclude. So, this homogenization of Markovian qubit dynamics, it has been shown using partial swap in the collisional model based upon ratio test for convergence of sequence. So, what other people have shown earlier, these Giza and others, Zeeman, so their method was not based on ratio test. Their method was something else. So, here we have used ratio test because this is what we wanted to use for both Markovian and non-Markovian case. Non-Markovianity in qubit dynamics, system qubit dynamics, has been obtained by using ancilla-ancilla interaction on the top of system-ancilla interaction via partial swap and also with partial s theta phi. And the case of partial swap type ancilla-ancilla interaction, universal homogenization happens. Universal means irrespective of initial state of individual path qubits. But that is not the case for partial s theta phi. Although we get a better rate, but we will have to sacrifice at this level. Now, we have also noticed that the rate of homogenization is always higher in the asymptotic limit than the partial swap. Depending upon the values of theta and phi and the initial ancilla state, the rate can be higher, almost same, or lower than the Markovian counterpart. With particular structure of system Hamiltonian, our study may help us in understanding thermalization process in non-Markovian scenarios. So, because we have used a particular type of interaction, maybe one can take some other interaction. So, we have some open issues here. So, we have seen that for specific choice of initial path state and specific choice of the parameter theta and phi corresponding to the path qubit, bath qubit interaction, so bath qubit interaction unitary S theta phi, the rate of homogenization of the system qubit can be even higher than the corresponding rate for the Markovian counterpart. We have also seen that those particular choice of eta, theta, and phi, it is not clear whether there is any signature of backflow of information because there is no jiggling, as I said. Okay. So how to justify? Because it is a phenomenological model of non-Markovianity because we are allowing bath qubit interaction. But in some cases of parameter values, we don't get to see the jiggling. That means there is no signature of back action. So what does it mean? So question is, how do I justify that in the case where bath qubit interaction is there, we indeed have a non-Markovian dynamics? So one can resort to some of these measures of non-Markovianity, BLP measure, which uses the trace distance, or RHP measure, which take the deviation from CP divisibility, or through dynamics of entangled state of the system and some ancillary, some other system. Unfortunately, we have checked with all these. None of these helps us to figure out that indeed, when we have specific choice of theta, phi, and eta, the dynamics is indeed non-Markovian. In fact, it tells actually that the dynamics can be Markovian. Okay, so this is the plot. So this is the BLP measure plot. So for different theta and phi, you see that so this is for a particular initial state of eta of the bath qubit, which is 0, and we have used this n 2000 iterations. And here you see that there is a valley on this side, there is also a valley on the right hand side, and there is a hump in between. So when there is a hump, this guarantees non-Markovianity because BLP measure is positive, but in this valley BLP measure is 0. So you can't say whether it is Markovian or non-Markovian. To have a better picture in the log scale, you can see that on the left hand side there is valley, on the right hand side there is valley, but in middle there is hump. So in the middle, so this is for theta and phi. In the middle, it corresponds to non-Markovian dynamics, but in the valley, it may correspond to Markovian dynamics. Okay, so the point is that it may happen that even if when we have bath-bath interaction of particular kind and initial state of bath to be a particular type, we may get to see Markovian dynamics. In other words, our suggestion is that we'll have to expand the notion of Markovianity in the collisional model from just the system bath interaction to include also, in some cases, bath-bath interaction. But whether this is actually Markovian or non-Markovian, we'll have to explore it further. In particular, we may have to figure out what is the dynamical equation of the system qubit, whether it is in a modified GKSL form, whether it is completely different form, whether one can figure out memory kernel, etc. So we don't know. So we'll have to figure out that. So with that, I conclude. Thank you.
Thank you, Professor Ghosh, for this interesting lecture on how classical models are being applied to study the Markovian and non-Markovian dynamics. So we thank you very much for this. If there are any questions, I open up the session for questions for Professor Ghosh. The participants can please ask the questions.
I have a question.
Yeah, please.
Yes.
So here in the homogenization of the non-Markovian system, the system
Yes.
and bath interaction and bath-bath interactions, the bath qubits interaction and the system and
Yes.
bath qubit interaction, does it depend on the time of interaction between the system and bath qubit?
Here we have not taken that time dependence, but in principle, you can also take that, which will make life more difficult. So here, the interaction that we have chosen is fixed. That means the duration of interaction is fixed, and the type of interaction, that means the Hamiltonian which will generate that unitary, is also fixed.
Okay. Okay.
But in principle, you can take that, but that will make life more difficult. Yes.
So it's like the system and the bath qubit is also like an equivalent. Does it?
Well, not equivalent. I mean, system and path qubit, they are interacting through what I said, partial swap. Okay. And why we took it partial swap? Because for the Markovian case, it is already known that unless you take it to a partial swap, homogenization will not happen. Okay, that people have already shown. So that is why we have taken it to be partial swap. But path qubit interaction, one can take anything. I mean, well, not anything on some form so that homogenization happens. We have taken a generalization of this partial swap, which is partial S theta phi.
S theta. Okay. Thanks.
Okay. Any more questions?
Yeah, can I ask?
Yeah,
question?
sure. Yeah.
Thank you for your talk. I have two clarification questions, but maybe I will ask one due to the time restrictions. So in quantum optics, people also use frequently Heisenberg-Langevin equation in addition to GKSL. So
Yes.
could you please share any advantages or disadvantages in using Heisenberg-Langevin approach as compared to GKSL?
Well, I have not worked with this Heisenberg-Langevin approach, but I assume that they can also work equally well. Maybe there may be some problem with the solution, but in principle, they can also work equally well. Okay. I mean, particularly in this case, when the case which I described, maybe this Langevin equation approach may be better, because here to figure out a master equation like GKSL kind or its modified form is quite difficult. I mean, you'll have to go to the continuum limit and all that, which becomes really difficult.
Okay. I think, can I ask second question, or shall I ask it in the chat?
We are running past time, and Dr.
Okay. Yeah, sure.
Waiting, so we can.
Yeah. Okay, so maybe the further questions can be taken up later. You can contact Professor Ghosh, or maybe the organizers can connect you up with him, share your questions. So thank you, Professor Ghosh, once again for this great talk. And now we move to our next speaker.